Well, I hope you had fun playing in our own backyard, the solar system, last week. We learned a lot of things. We saw ways to apply the physics we learned, but we want to broaden our horizons beyond that. And if we look back at Athens and that dark field back in November, we were looking at the moon and at Jupiter, but most of what we saw out there was the stars with their various colors and brightnesses. And we're going to spend this week, indeed, taking the first step beyond the solar system, and that's going to involve trying to understand the stars. I think it was Auguste Comte who said that we're very limited as regards the stars. We can look at them, but we can't touch them, and we can't smell them, and we can't taste them, and we can't do any experiments with them, so how are we ever going to figure out what's going on and what stars are made of or how they work? And there are two things that I would add, two places where Comte was wrong. One is, we've learned, as we'll see, to look very closely and in ways that he couldn't have imagined. And the other thing we can do is we can think about stars. We can bring to bear all of the physics we've learned and perhaps even some new physics. And that's what we're going to spend this week doing. Use all of those things to see what we can say about stars. And so here's the plan. Of course, natural place to start, just as we started our discussion of planets with Earth, is to start our discussion of stars by looking at the sun, our local star. We have a lot more observations of the sun than we do of other stars. It's a good place to develop an understanding, and as we'll see, that'll take us to some new physics. And then, once we want to look beyond the sun at other stars, we need to start figuring out how to measure things about the stars. What do we want to know? We want to know their luminosities. We want to know their temperatures. We want to know their sizes and masses so that we can parameterize our understanding of the physics by matching it to the observed parameters of the models. And then, at the end of the week, we will take all of those things that we will learn you can measure for all these stars and look at the statistical distribution of such things and use the information from that, or review how people use the information from that, to refine a set of stellar models that give us a pretty deep understanding of what goes on inside stars. That said, we move on, we start by talking about our sun, and immediately we bump into a problem. What's the most salient thing about our sun? The most salient thing about our sun is that it shines. It produces these 4 times 10 to the 26 watts of energy. It does that, we know, because it's a large, hot object at 5,800 degrees with that surface area. It radiates that much. So far, so good. It's radiating that energy. It's been doing it for 4.5 billion years, and the question is, why is it not cold yet? Why is it still at 5,800 degrees on the surface? And one can start assessing the ways we know of producing energy. And the way we usually produce energy, is various chemical reactions. The common factor between all of these is that all chemical reactions involve rearranging the electrons in an atom. Rearranging the electrons in an atom is essentially forming the electromagnetic potential energy in atoms. Because of the size of an atom and the size of the charges, this produces on the order of 10 to the minus 19 joules per atom. And if the atom in question is a hydrogen atom, which is what the sun is made of, and I'm not saying that I can propose a way to chemically burn hydrogen in the absence of oxygen, but imagine that there were some bizarre chemistry that takes place at solar temperatures or something. It would produce this much energy. Figure out that there are 6 times 10 to the 23 hydrogen atoms in a gram, and you find that a kilo of hydrogen would produce about 6 times 10 to the 7 joules. 60 million joules is a lot of energy, but the sun produces 10 to the 26 joules every second, so you'd need to burn about 6 times 10 to the 18 kilos of hydrogen per second to power the sun by chemical forces. You'd run out of energy in about 10,000 years. It was this idea that led Lord Kelvin to the idea of Kelvin-Helmholtz heating. The process that we've been seeing is very important in astrophysics. This involves converting to heat the gravitational potential energy from the collapse of the solar nebula that formed the sun. We did an estimate of this in the homework. There will be solutions at some point if you didn't do it. And indeed, you produce a lot more energy that way than you ever would by burning hydrogen or any other chemical reaction. But the gravitational potential energy that the sun liberated by condensing to form a star would only last about 10 million years. This is great. The sun has been doing this for 4.5 billion years. And our first question is going to be, a very important one, how does the sun shine? Where does the energy come from? That, of course, will take us to more new physics, and we'll take it from there.